Okay, so have you ever had that feeling where you're like really trying to understand something complex,
Hmm.
but there's just like so much information out there?
Yeah,
It's like you just want to like cut through the noise and get right to the core ideas.
absolutely.
Well, that's what this deep dive is all about today.
I like it.
We are tackling a paper that's been hugely influential in AI.
This is a big one.
It's called Attention is All You Need.
From Google.
And it
Yeah.
introduced this like totally new network architecture called the transformer.
Yeah.
And what's so cool about it is it really addressed some of the, big problems that we were facing with how computers process sequences, like, when you're translating languages
Yay.
or trying to understand speech or even like generating text.
Yeah, like how do you get a computer to understand a sentence as a whole?
Right.
Not just one word at a time.
Yeah. And for a long time, we were relying on these methods like recurrent neural networks and convolutional neural networks.
Yeah, they had their limitations.
They weren't perfect, right?
No, they weren't perfect.
So what we want to do today is really unpack the central ideas behind the transformer.
Okay, sounds good.
Like, why was it such a big deal?
Yeah. Why did it change everything?
And we'll try to do this without, like, getting bogged down in all the crazy technical jargon.
Yeah, we want to make this understandable.
Exactly. So let's rewind a bit.
Okay.
Before the transformer, how were computers handling these sequence-based tasks?
Well, basically, the king of the hill was RNNs,
RNNs.
recurrent neural networks.
Okay.
And you've probably heard of some of the specific types like LSTMs,
LSTMs.
long short-term memory networks,
Okay.
or GRUs, gated recurrent units.
Okay, so these were like the main tools everyone was using.
Yeah, pretty much.
So how did RNNs actually like work? What was their whole deal?
So they processed information sequentially.
Sequentially.
Yeah, one element at a time.
One at a time.
Yeah, so think about like reading a sentence.
Okay.
The RNN would look at the first word.
Understand it, then use that to understand the second word,
Got it.
and so on.
Step by step.
Yeah, exactly.
Okay, and the paper really highlights how this sequential nature was kind of a major roadblock.
A bottleneck for sure.
What was the biggest problem with that?
Well, because each step depends on the one before it.
Yeah.
You can't really speed up the training process very much,
Especially for longer sequences, I imagine.
especially for longer sequences.
Yeah.
Like a whole book?
Yeah, imagine trying to train a model on War and Peace. You
Right.
can't just process all the chapters at the same time.
You need that context.
Exactly. And this made it really slow and inefficient.
And I guess also with longer sequences, you run into memory problems
Oh, yeah. Yeah.
if you're trying to process too much at once.
Yeah, your computer just can't handle it.
So it limits how much you can do at the same time.
Exactly.
Now, people did come up with some clever ways to like tweak RNNs and make them a bit better, right?
Oh, yeah, definitely. There were all sorts of tricks like factorization and conditional computation. These helped a bit, but
But the core problem was still there.
yeah, you couldn't escape that sequential processing.
So the paper also mentions convolutional neural networks, or CNNs,
Right.
as another kind of approach people were exploring for sequences.
Yeah.
So how did CNNs fit into this whole pre-transformer world?
Well, CNNs were interesting because they offered a way to do more parallel processing.
Okay.
They could look at different parts of the sequence at the same time
Yeah.
using these things called filters.
Okay.
But the problem with CNNs was understanding those really long-range relationships in a sequence,
Okay.
like how the first word connects to the last word.
Right.
To do that, you needed to stack a ton of convolutional layers.
Okay.
And the more layers you added, the harder it became to actually learn those long-distance connections.
So it's like a trade-off, right?
Yeah.
You get parallelism, but then it's harder to connect those distant elements.
Exactly.
Interesting. Okay, so we've got RNNs, which are slow, but can handle long-range dependencies.
Mhm.
And then we have CNNs, which are faster, but struggle with those long-range connections.
Yeah, that's a good summary.
So enter the transformer.
Ta-da.
And a key concept here is attention.
Yeah, attention is the magic ingredient.
But attention mechanisms weren't like a brand new thing when this paper came out, right?
No, they weren't entirely new.
People were already using them,
But they were mostly using them with RNNs.
Okay, so it was like an extra thing.
Yeah, like a little helper
Okay,
to help the RNN focus on the most important parts of the input
got it.
as it was processing the sequence.
Okay.
Kind of like a spotlight
Okay.
shining on the important bits.
Got it. Okay, so what was the really radical idea that the transformer brought to the table?
So the big revolutionary idea was this.
Okay.
They got rid of both recurrence and convolutions completely.
Whoa.
Yeah, they said, we're going all in on attention.
Just attention. That's a pretty bold move.
It was a huge gamble.
So the paper mentions this really important advantage of this attention-only approach,
Yeah.
that it can connect those distant positions in a sequence with a constant number of operations.
Right, because with RNNs, the number of steps grows with the length of the sequence.
Right.
But with the transformer, it's always the same.
It doesn't matter how far apart those elements are.
Exactly. It's super efficient.
Now, I guess one might think that if you're just jumping around connecting distant elements, you might lose some of that, like, fine-grained local context that you get with sequential processing.
Yeah, that's a valid concern.
This is where multi-head attention comes in, right?
Exactly. Multi-head attention lets the model look at those relationships in multiple ways at the same time.
Okay, so it's not just jumping around randomly. It's looking at those connections from different angles.
Exactly.
Cool. Okay. And the paper also introduces this idea of self-attention.
Sometimes called intra-attention.
Okay, so what's that all about?
So self-attention is basically about understanding the relationships between different parts of the same sequence.
Within the same sequence.
Yeah, so like in the sentence, the cat sat on the mat, self-attention would let the model see how cat relates to sat
Okay.
and how the relates to cat.
Within that same sentence.
Exactly.
Okay. And this helps the model build up a really rich understanding of the whole sentence.
Yeah, it's like figuring out the internal structure of the sentence.
Right. And self-attention wasn't like a completely new idea at this point, right?
No, it had been used before for things like reading comprehension and text summarization.
Sure.
But the transformer was the first model to really use it for transduction tasks.
Transduct.
Yeah, like translation.
Okay.
Where you're taking one sequence and transforming it into another.
So it's not just understanding a single sequence. It's
Yeah.
about transforming it.
Exactly.
And the transformer did this entirely with self-attention.
No RNNs or CNNs needed.
Wow, that's pretty groundbreaking.
It was a big departure from the way things were done.
Okay, so we've talked about the limitations of the old methods and the core idea of attention.
Right.
Now let's get into the architecture of the transformer itself.
Let's crack it open.
It's described as an encoder-decoder structure, which is like a common pattern for these sequence-to-sequence tasks.
Yeah, it's a classic setup.
So can you walk us through like the basic layout?
Sure. So the encoder-decoder structure is kind of like a two-step process.
Okay,
The encoder takes the input sequence,
let's say an English sentence.
right, an English sentence, and it basically crunches it down.
Crunches it down.
Yeah, it creates like a condensed representation of what that sentence means,
Okay,
kind of like summarizing it.
okay,
And then the decoder takes that summary
okay.
and uses it to generate the output sequence.
Which would be like the translated German sentence.
Exactly.
Okay, so the innovation of the transformer is in how it implements these encoder and decoder parts, right?
Right.
And the paper talks about using these stacked self-attention layers.
Yes.
So what's the deal with this stacking?
So both the encoder and the decoder are made up of multiple layers.
Okay.
And these layers are identical.
Identical.
Yeah, they're all the same. And they're stacked one on top of the other,
Like pancakes.
kind of like pancakes.
Okay.
And the base model they describe in the paper uses 6 of these layers.
This layers.
6 layers in both the encoder and the decoder.
Okay, so it's like a 6-layer stack for each.
Exactly.
Okay, and what's the point of having all these layers?
Well, each layer allows the model to learn more and more complex patterns in the data.
Okay.
So as the information flows through the layers,
Okay.
it gets refined and the model's understanding of the input gets deeper.
So it's like each layer builds on the previous one.
Exactly.
Okay, so let's break down the encoder first.
Right.
What are the main components of each of those 6 layers?
So each encoder layer has 2 main parts.
Okay,
The first is the multi-head self-attention mechanism.
which we'll talk about more later.
Yes, definitely.
Okay.
And the second is a position-wise feed-forward network.
Position-wise feed-forward network.
Yeah, it's a bit of a mouthful.
Okay, and this feed-forward network helps to further process the information at each position. Okay, and then the paper mentions these things called residual connections and layer normalization.
Yeah, those are important too.
They sound kind of like extra steps.
So residual connections are basically shortcuts.
Shortcuts.
Yeah, they let the original input to a layer bypass the layer and get added to the output.
Got it.
It's like a little detour.
Okay, why do you need that?
Well, it helps information flow more easily through the network,
Okay.
especially in really deep networks.
Okay.
It prevents a problem called vanishing gradients.
Vanishing gradients?
Yeah, it's a problem that can happen when you have a lot of layers.
Okay.
The gradients can get really small, and it makes it hard to train the model.
So the residual connections help with that.
Exactly.
Okay. And what about layer normalization?
Layer normalization is another trick.
Okay.
It helps to stabilize the learning process
Okay.
by normalizing the outputs of each layer,
Okay.
so the values are kind of in a consistent range.
Got it. So it's all about making the training process smoother.
Exactly.
Okay. And the paper also mentions that all these layers in the embeddings maintain a consistent output dimension of 512.
Yes, D model equals 512.
Okay. Why is that important?
Well, it's mainly because of those residual connections.
Okay.
To add two vectors together, they need to have the same number of elements.
Right.
So by keeping the dimension consistent throughout the model, you can just add the outputs of different layers together.
Makes sense. Okay. So we've covered the encoder.
Yeah.
Let's move on to the decoder.
Okay.
How is it similar to the encoder and how is it different?
So the decoder is very similar to the encoder in a lot of ways.
Okay.
It also has those stacked layers.
Okay.
It uses multi-head self-attention.
Okay.
It has those position-wise feed-forward networks.
Okay.
And it uses residual connections and layer normalization.
Okay. So it's got all the same bells and whistles.
Yeah, but it also has one extra special ingredient
What's that?
and an additional third sublayer.
Okay. A third sublayer. What does it do?
So this third sublayer also does multi-head attention. But instead of looking at the decoder's own previous layer,
Right.
it looks at the output of the entire encoder stack.
Oh, interesting. So it's like connecting the encoder to the decoder.
Exactly. It's the bridge between them.
Okay.
It lets the decoder focus on the relevant parts of the input.
As it's generating the output.
Right.
So it's kind of like the attention mechanisms in those older models with RNNs.
Yeah, it serves a similar purpose.
But it's all done with attention.
No RNNs needed.
Okay, and there's another important difference with the decoder's self-attention, right?
Yes.
This masking thing.
Right.
Why is masking necessary specifically in the decoder?
Well, the decoder has to generate the output sequence one word at a time.
Word
It's like writing a sentence.
Okay.
You can only see the words you've already written, not
Right.
the words that come later.
Okay.
So masking prevents the decoder from cheating.
Cheating
Yeah, it stops it from peeking ahead at the future words in the output sequence.
during training.
Right during training.
Okay, so it's like making sure it's playing by the rules.
Exactly.
Okay, so we've got the encoder, which processes the input,
Right.
the decoder, which generates the output step by step.
Yeah,
And they're linked by this attention mechanism.
the bridge.
Okay, now let's dive into attention itself.
Okay.
The paper defines it as this mapping of queries, keys, and values.
Right.
Can you unpack that a bit for us?
Sure. So an attention function takes three things as input.
Okay.
A query, a set of keys, and a set of values.
Okay.
And the output is a weighted sum of those values.
Okay.
But the weights are determined by how well the query matches each key.
Okay, so it's like you're searching for something. The query is what you're looking for.
Right.
The keys are like the labels on the boxes.
Yeah, good analogy.
And the values are what's inside the boxes.
Exactly.
So the better the match between the query and the key, the more weight that value gets.
Right.
Okay. And the transformer uses a specific type of attention called scaled dot product attention.
Yeah, that's their special sauce.
So what makes it different?
Well, it uses the dot product to measure how similar the query is to each key.
Okay.
And then it scales those dot products by dividing by the square root of the key dimension.
Okay. Why the dot product and why the scaling?
So the dot product is a way to measure how much two vectors point in the same direction.
Okay.
And the scaling is important to keep the values from getting too big.
Okay. Why does that matter?
Because if the values get too big, the gradients can become very small.
Gradients.
Yeah, the things the model uses to learn.
Okay.
And if the gradients are too small, the model learns very slowly.
So it's all about making sure the model can learn effectively.
Exactly.
Okay. And they also mention using matrices instead of individual vectors.
Yeah,
That's for efficiency, right?
exactly. It's much faster to do matrix multiplication than to calculate everything individually.
Especially on GPUs.
Right. GPUs love matrices.
Okay. Now, building on this scaled dot product attention, the transformer uses multi-head attention.
Multi-head attention.
Yeah. What's the idea behind having these multiple heads?
So the idea is that instead of just doing one attention operation,
Oh, yeah.
you do multiple attention operations in parallel.
Okay.
But each head looks at the data in a slightly different way.
Okay. So it's like having multiple experts.
Yeah, like a team of specialists.
Okay. Each with their own perspective.
Exactly.
And then you combine all their insights.
Right. You take all the outputs from the different heads and put them together.
Okay. So why is that better than just having one head?
Well, with one head, you might miss some important information.
Got it.
Like maybe one head is really good at understanding the grammar,
Okay.
and another head is really good at understanding the meaning.
Okay.
So by having multiple heads, you get a more complete picture.
Makes sense.
Okay.
So how is this multi-head attention used in the transformer?
So they use it in three main ways.
Okay.
The first is in the encoder-decoder attention layers.
Okay.
This is where the decoder focuses on the relevant parts of the input.
Right.
The second way is in the encoder's self-attention layers. Here, each word in the input can attend to all the other words in the input.
So it's understanding the relationships within the input sentence.
Right.
Okay.
And the third way is in the decoder's self-attention layers.
Okay.
And this is where masking comes in
Right.
to make sure the decoder doesn't cheat.
Okay. So it's all about using attention in different ways
Right.
to understand the relationships within the input, within the output, and between the input and the output.
Exactly. It's all about connections.
Okay. So we've covered the attention mechanisms.
Right.
What other important parts are there in the transformer architecture?
So there's also the position-wise feed-forward network.
Right. We mentioned that before.
Yes.
So what does it actually do?
It's a fairly simple neural network that's applied to each position in the sequence independently.
Okay.
It basically takes the output of the attention layer
Okay.
and applies two linear transformations with a ReLU activation in between.
Okay.
So it's like a little processing step.
Okay. And what's the point of this extra processing?
It helps the model learn more complex features,
Right.
and it adds nonlinearity.
Nonlinearity.
Yeah, neural networks need nonlinearity to be able to model complex relationships.
Makes sense. Okay. And then there's embeddings and the softmax layer.
Right, those are standard components.
Okay.
Embeddings are used to convert the words into vectors,
Right.
so the model can work with them.
Okay.
And the softmax layer is used at the end of the decoder
Okay.
to predict the probability of each word in the vocabulary.
Okay. And the paper mentions weight sharing between the embedding layers and the softmax layer.
Yeah, that's a trick to reduce the number of parameters in the model,
Okay.
and it can improve generalization.
So it's like making the model more efficient.
Yeah, and more robust.
Okay. So we've got all these pieces now.
Yeah,
But the transformer doesn't process things sequentially like RNNs.
right.
So how does it know the order of the words in a sentence?
That's a great question.
Like, how does it know that the cat sat on the mat is different from the mat sat on the cat?
Well, that's where positional encodings come in.
Positional encoding.
Yeah, they're like little flags.
Flags.
Yeah, that tell the model where each word is in the sentence.
Okay.
They're added to the word embeddings.
Okay.
So the model has both the meaning of the word and its position.
Okay. And how are these positional encodings created?
So they use sine and cosine functions.
Sine and cosine.
Yeah.
Okay.
They create these wave patterns,
Okay.
and each position in the sentence gets a unique pattern.
Okay. So it's like a wave signature for each position.
Exactly.
Okay. Why sine and cosine?
Well, they hypothesized that this would make it easy for the model to learn relative positions.
Relative position.
Yeah, like how far apart two words are, because
Yeah.
you can represent the positional encoding of one position as a linear function of the positional encoding of another position.
Okay. That's pretty clever.
It is.
And they also learned positional embeddings, right?
Yeah, they did.
But they stuck with the sine and cosine ones.
Yeah, they found that the sine and cosine ones worked just as well. Okay.
And they might generalize better to longer sequences.
So it's like a more future-proof choice.
Exactly.
Okay, so we've gone through the whole architecture now.
We've built a transformer.
Let's circle back to why this whole approach is so powerful.
Right.
The paper highlights three main advantages.
Yeah.
What are those?
So the first one is computational complexity.
Okay.
Self-attention is actually faster than RNNs for sequences where the length is smaller than the dimension of the embeddings.
Which is often the case.
Yeah, especially with modern NLP models.
Okay.
Now, for super long sequences, self-attention can become a bit slow
Okay.
because it has to look at all the pairs of positions.
Right.
But the paper suggests you can fix that by restricting the attention to a local window.
Okay, so you don't have to look at everything.
Exactly.
Okay, what's the second advantage?
Parallelization.
Parallelization.
Yeah, self-attention can be parallelized really well.
Because you can process all the positions at the same time.
Right,
Okay, and that makes training much faster, especially on GPUs.
right.
RNNs are much harder to parallelize.
Because they have to process things sequentially.
Exactly.
Okay, and the third advantage.
Long-range dependencies.
Okay.
The transformer can connect distant positions in a sequence really easily.
Because the path length is always short.
Right.
Okay, and CNN struggle with that.
Yeah, they need more and more layers to connect distant positions.
So the transformer is faster, better at long-range dependencies, and more efficient.
That's a good summary.
And the paper also mentions this cool side benefit,
Yeah,
interpretability.
right.
You can actually visualize the attention weights.
Yeah, you can see what the model is paying attention to.
And they show some examples in the appendix, right?
Yeah, they have some cool visualizations.
Okay, so we can get a glimpse into the black box.
Yeah, it's not completely opaque anymore.
Okay, so the transformer architecture brings all these benefits.
Yeah, it's a game changer.
Now let's talk about how they actually trained these models.
All right.
What kind of data did they use?
So for their main experiments, they used two big machine translation data sets.
Okay.
The WMT 2014 English to German data set
Okay.
and the WMT 2014 English to French data set.
And these are like standard benchmarks.
Yeah, everyone uses them.
Okay.
So it's easy to compare results.
Okay, and how do they handle the training process?
Well, they batched the data.
Batched it.
Yeah, they
Yeah.
grouped the sentences together into batches,
Okay.
and they trained the models on 8 NVIDIA P100 GPUs.
8 GPUs.
Yeah, they needed a lot of computing power.
Makes sense.
The base models trained for about 12 hours,
Okay.
and the bigger models trained for about 3.5 days.
3.5 days. That's a
Yeah.
lot of training.
It is.
Okay, what about the optimizer and the learning rate?
So they use the Atom optimizer.
Had 'em.
Yeah,
Okay.
and they use a special learning rate schedule
Okay.
where they increased the learning rate linearly for the first 4,000 steps
Okay.
and then decreased it gradually after that.
Okay, why did they do that?
Well, it's a trick that's been found to work well for transformers.
Okay.
It helps the model converge faster and find a better solution.
Okay, and what about regularization?
They used residual dropout and label smoothing
Okay.
to prevent overfitting.
Overfitting.
Yeah, where the model learns the training data too well
Okay.
and doesn't generalize well to new data.
Right, so these techniques help the model be more robust.
Exactly.
Okay, so after all this training, how did the transformer actually perform?
The results were amazing.
But amazing.
Yeah, they blew the previous state-of-the-art out of the water.
Wow. Huh? Tell me more.
So on the English to German task, their big model got a BLU score of 28.4.
28.4.
Yeah, which was more than 2 points higher than the previous best result.
That's a huge improvement.
It is.
And what about English to French?
On English to French, they got a BLU score of 41.8.
41.8.
Yeah,
Wow, so they really dominated both benchmarks.
they did.
And the paper has a table that shows all the results, right?
Yeah, table 2.
It really highlights how much better the transformer is.
Yeah, it's a very clear comparison.
Okay, so they also tested the transformer on a different task, right?
Yeah, English constituency parsing.
Okay, what is that?
So it's about analyzing the grammatical structure of a sentence
Okay.
and building a tree that shows the relationships between the words.
Okay, so it's like diagramming a sentence.
Kind of like that, yeah.
Okay, and why did they choose this task?
Well, it's a very different kind of task from machine translation,
Okay.
and it's a task where RNNs hadn't been very successful.
Interesting.
So they wanted to see how well the transformer would generalize.
Okay, and how did it do?
It did surprisingly well.
Surprisingly well.
Yeah, it got an F1 score of 91.3 on the Wall Street Journal dataset.
91.3.
Yeah, which is better than the Berkeley parser.
Okay, that's impressive.
And in a semi-supervised setting, they got an F1 score of 92.7.
92.7.
Yeah.
Wow,
Yeah.
so even without much task-specific tuning, it was really good.
Yeah, it shows that the transformer is very adaptable.
Okay, so as we wrap up this deep dive, what's the big takeaway here? Why is the transformer such a big deal?
Well, I think the biggest thing is that it represents a fundamental shift in how we think about sequence processing.
Oh.
It moves away from sequential models like RNNs
Okay.
and towards attention-based models.
Okay.
And attention turns out to be a really powerful way to model relationships in sequences.
Yeah, it's like a whole new paradigm.
Exactly.
And it's not just about language either.
All right.
It has implications for all sorts of AI tasks.
Yeah. Anything that involves sequences.
So I guess a question for you, our listener, is this.
Okay.
Where else could attention be applied?
That's a good question.
Like what other areas could be revolutionized by this kind of thinking?
Yeah. Think beyond language.
Image processing,
Yeah.
audio analysis, understanding complex systems.
Absolutely.
It's really exciting to think about.
It is.
And the authors of the paper also hint at some future directions in their conclusion,
Right.
like extending the transformer to other modalities.
Yeah, like images, audio, and video.
And finding more efficient attention mechanisms.
Yeah, for really long sequences.
And making the generation process less sequential.
Yeah, that could lead to even faster models.
So the research is still ongoing.
Oh yeah, there's so much more to explore.
And if you're interested in digging deeper into the technical details,
Yeah.
the authors have made their code available on GitHub.
It's on the TensorFlow Tensor2 Tensor library.
You can find the link in the show notes.
Yeah.
I think the success of the transformer is a really inspiring example of what can happen when you challenge the status quo.
Absolutely.
Sometimes the biggest breakthroughs come from questioning the fundamental assumptions.
Yeah, it's about thinking outside the box.
And Transformer definitely did that.
It changed the game.
And who knows what other amazing discoveries are waiting to be made.
Yeah, the future of AI is wide open.
It's an exciting time to be in this field.
I couldn't agree more.
All right, that's it for this deep dive.
Thanks for having me.
Thanks for joining us.
It was fun.
Until next time.
See ya.